Hello, I'm Pam Hoffman, Everyday Spacer.
I'm Jeff Miller, 2049 Outfitters.
At Everyday Spacer, we show regular folks how to personally and directly participate in space exploration, science, and astronomy. We're here on Friday nights at 9 p.m. Pacific Time, 5 a.m. on Saturday in London, and 6 a.m. on Saturday in Germany. We're broadcasting live from Thousand Oaks, California. And we have comments.
Yep. Janie Becker says,
Awesome.
Fired up to learn tonight.
Cool. Welcome. Thanks for being here.
And so is Dawn.
Likewise, Dawn. Thank you so much. We really appreciate you participating. Thanks so much to all of our participants and subscribers. Over 85% of our viewers have not subscribed, though. If you watch 2 or more episodes, please consider subscribing.
Oh, and Dawn says, hi, folks. And Scott says, hello. Hello, everyone.
Hey, Scott. Welcome. Yep. Thanks for joining us, folks. You're up.
Oh, yeah.
Right here.
Tonight's... Oh, yeah, there's something for me to do here other than look at comments. Okay. Hi, guys.
That's okay. I almost forgot my name at the very top, so you're allowed.
Okay, so tonight's crunchy topic is fire in space. We'll be back in 8.3 seconds. There's a link to that book in the description. And last week, longtime viewer and participant Janie Becker, the Encourager, had some ideas for an episode. So thanks to Janie, tonight we'll delve into fires in space, temperatures on asteroids, and generally talk about heat and temperature. They are different beyond Earth's stabilizing atmosphere in this crunchy topic show. Fire is pretty exciting on Earth. What happens in space, Pam?
Fire works a little bit different in a microgravity environment on a space station, so a little more specific than just in space. I remember the very first time I learned about fire in space, I watched a video created by cosmonauts on the Mir space station. And I actually found that video during this past week. Let's start there. As we're watching this, I want you to note several things. Number 1 is the flame. Number 2 is the air or oxygen, or maybe lack of oxygen, and the molten wax.
Yeah. Yeah. Also, just note that in all of these videos, it takes place in an atmosphere. Because if you're in the vacuum, there's no oxygen to burn unless you burn your own.
That's true. That's true. So yeah, there is in fact an environment. It's just space versus the planet. All right. So I've got the first one up. You want to go ahead and share that? And most of these are really short. I will play some of them. And some of them I don't play. I'll make sure you know how to find them. So this is the actual video that I remember from years and years ago. I love the Russians. They did so many cool things in space. And this is one of them. They burned this little candle shaped like a bear. Did you mute it? No. Okay. Yeah, I don't think NASA scientists would get away with this. I don't know enough Russian to understand what they're saying.
But just look at the dome shape instead of a normal flame shape.
Until he blows on it, giving it more oxygen.
Yep. And a direction.
Yeah. This just amuses me so much. They've got a candle with a live flame on a space station. But it works very differently. And I've got some videos that will cover that a bit more. But fire is kind of an interesting thing because it takes like 3 things for it to really happen. Fuel and oxygen and heat.
There are some cases where something else can substitute for oxygen, but we don't, those are rare enough that they won't happen on Earth. Hey, Janie. Yep.
Yes, it is.
Yeah. Yeah, if you notice that dome shape, it's because there's no gravity for heat to rise.
Yeah, we've got some videos on what's happening there and why.
Okay.
But I really liked some of these. I wanted to go ahead and share them with you. These shorts are really short, so.
Can it ever be just physically too cold to start and maintain a fire?
Oh, thank you for asking, Eons. The short answer is yes. It can absolutely be too cold to start a fire.
Because remember, we need heat. That's one of the 3 things we need to have a fire.
Needs 3 things to start: oxygen, fuel, and heat. If
And
you're
there's our
missing
triangle.
1/3 of the equation, you're out of luck. A flame will only start if the fuel source gets to the ignition temperature that it needs. But what that temperature is depends on things like the size of the particles and the fuel source you're working with. Smaller particles have more surface area for their volume compared to larger particles, so they're easier to light, resulting in a lower minimum ignition temperature. But the oxygen and fuel ratios also affect that minimum temperature. So gasoline, for example, needs to be at least negative 43 degrees Celsius depending on those factors. If that threshold isn't reached, the particles will not be moving fast enough to ignite and start a flame, so the warmth just dissipates into the surroundings.
All right, so. And the Chinese went and reproduced this experiment by the Russians, also with an open candle. Just fascinating to me that these other countries would have open flame in their space stations. And they don't speak English either, so.
I like the fact that they put that background behind it so that you can see the difference in the flame between.
And now you've got a comparison as well. So I wanted to, this is kind of longer, 1:11, but this part was the most important part. And then this guy has, I like his explanation a lot too. And he talks about, anyway, I'm just going to run it. Go ahead and take a listen.
Everybody is familiar with this. The flame heats up the air and the light air is transported upwards. From below, there is the cold air coming, supplying the flame with oxygen. But did you know that this is only the case on Earth due to gravity? In space, there is no up and down, so the warm air cannot move away. This leads to the spherical shape of the flame with a limited supply of oxygen. This difference is actually a big challenge concerning fire safety in human spaceflight. In recent experiments, we found out that on a spacecraft, the flame burns weaker and will spread much slower, which is good. But on the other hand, the flame can be locally hotter, produces more toxic smoke, and is much harder to detect. This research helps to better understand fire under zero gravity and to make future exploration missions safer.
Yeah, one of the things, show us as well. One of the things that you'll notice is with some of these videos, you can't even see a flame. So if in fact there is fire and you can't see it, you don't know that you have to deal with it. Mm-hmm. And, it does act a little different in a microgravity environment, but yeah, you definitely have a very different kind of a thing going on with fire than you have on Earth. It's much easier to see it. Oh, and this was a pretty cool experiment. And this is Physics Girl. They actually dropped a box with a candle in it and took pictures of it on the way down. It's a little bit long. I'm going to go ahead and grab that link for you.
So it was a way of getting 0 G on Earth.
Right.
They dropped it, and therefore everything was falling at the same time.
Yeah, they got a certain amount of the same kind of effect. Yep. I don't think it was as obvious. Okay, here we go. So there's the link. It should be clickable for you.
Yeah, and that's 6.5 minutes long, so we're not going to run it for you, but it's very good.
Right. Yeah, I really enjoyed learning about it, and they have a fun attitude about it too. So this guy, he's a little bit more frenetic, and yeah, he's pretty excited, which is good. I really like it. He does take a lot of his material from this other video too. So I'm going to go ahead and give you that link. I think it's worth watching, especially if you want to stay awake. He's definitely very excited. And then this is kind of where he gets his source. And I've got this. It's a little bit of a pictorial demonstration of how this works. I'll grab this in a minute too.
Combine with oxygen to produce light, heat, carbon dioxide, and water. Some of the hydrocarbon fragments form ring-shaped molecules called polycyclic aromatic hydrocarbons, and eventually soot. Soot particles can themselves burn or simply drift away as smoke. The familiar teardrop shape of the flame is an effect caused by gravity. Hot air rises and draws fresh, cool air behind it. This is called buoyancy, and is what makes the flame shoot up and flicker. But what happens when you light a candle, say, on the International Space Station? In microgravity, flames burn differently. They form little spheres, says Williams.
Yeah, this is a very, very good contrast between the two. You don't have this oxygen replenishment in the bottom of the flame, so it just kind of smolders.
Space station flame balls turn out to be wonderful mini-labs for combustion research. Unlike flames on Earth, which expand greedily when they need more fuel, flame balls let the oxygen come to them. Oxygen and fuel combine in a narrow zone at the surface of the sphere, not hither and yon throughout the flame. It's a much simpler system. Recently, Williams and colleagues were doing a space station experiment called FLEX to learn how to put out fires in microgravity when they came across something odd.
Yeah, this is going to be very important, especially when you can't see the flame. You want to know how to put it out.
Small droplets of heptane were burning inside the FLEX combustion chamber. As planned, the flames went out. But unexpectedly, the droplets of fuel continued burning. That's right, burning without flames, says Williams. At first, we didn't believe it ourselves. In fact, Williams believes the flames are there, just too faint to see. These are cool flames, he explains. Ordinary visible fire burns at a high temperature between 2200 and 3100 degrees Fahrenheit. Heptane flame balls on the space station started out in this hot fire regime. But as the flame balls cooled and began to go out, a different kind of burning took over. Cool flames burn at the relatively low temperature of 400 to 1000 degrees Fahrenheit, says Williams. And their chemistry is completely different. Normal flames produce soot, carbon dioxide, and water. Cool flames produce carbon monoxide and formaldehyde. Similar cool flames have been produced on Earth.
How fascinating is that? It's actually a different chemistry even.
And here's the thing: is that while the products of a normal flame aren't great, the water's not too bad, but the carbon dioxide, you can't breathe it. You breathe it out. Soot, not great for you, but it's not. But flame in space, carbon monoxide, which replaces oxygen and binds itself to the red blood cells.
Not good.
And formaldehyde, which is not good for you either.
Yeah.
So flames in space actually produce poison.
Yeah. So I just thought that was fascinating, especially the idea that you can have a fire without being able to see the flame.
Well, yeah, it's like a pure alcohol fire can in the right circumstances be invisible.
Yeah, you were telling me about that. Go ahead and big fire, and then talk about what you mentioned before. That was fascinating. I didn't know that was even a thing.
Yeah, because there was a case of a racer who, at the time when they were using alcohol for fuel, got dosed in alcohol and was actually on fire, but no one knew that he was on fire. And he essentially burned to death before anyone knew what was happening.
Sounds like a really bad way to go.
Yeah, but the flame was cooler, but still, 400 to 1000 degrees. That's not something that you want to be in. So, no one knew he was dying because of that. Yeah.
Oh.
Yeah. Well, if you can see infrared, because
is it infrared?
Hot.
It would be hot.
Anything hot. Yeah.
Right. And I think it would be interesting to see that around a human person, human body, because they have kind of hot zones in the middle of them. Whereas if this were all hot, depicting the flame, that might be an indicator.
Well, even 400 degrees, which is the low, is still much hot, and that's Fahrenheit. It's still much hotter than a human runs.
Right, but I'm just seeing some of the infrared pictures of like you put your hand there or your face or whatever, and you've got kind of a spectrum of colors, but this might be
I think the human would be
really
kind of
hot.
hidden in it.
Oh, yeah, that's what I'm thinking too.
Yeah.
It would be more, you would see more of that uniform flame, but very, very hot.
It'd be like a special effects ghost.
Okay.
You know, there's a white spot, or, you know, basically, you know, where human shaped white spot.
Very good point there. That is spooky.
Yeah.
All right, so they do, go ahead and put it back on because they did some experimenting on the 0G
The vomit comet.
Zavava comet, yeah. And I don't know that these were, I was going to grab this one for you too, wasn't I? Here, let me get that link. Copy. Because this one had the butane lighter behind it, so I don't know that it was as good as having the candle, which has the fuel there, and it just wicks up into the.
Yeah.
It is a wick, and that's why
Right.
what it does too.
Because instead of rising heat pulling the flame up, they've got butane pushing the flame up. I
Yeah.
mean, so it's not.
So I'm going to run just a little tiny bit of this.
Then we'll try it in 0G, and it should be.
We will see.
We will see.
We take it for granted that flames have this distinctive shape, but that's only because of gravity. The products of combustion have more energy, and so move around faster and take up more space than the cooler air around them. Therefore, there's a buoyant force on them which is greater than their weight, and so hot air rises. This helps pull in the oxygen from around the flame to continue the reaction.
We're going through hyper-G. I keep blowing out the candle because the stress of hyper-G is significant.
In hyper-G, this effect is magnified, since the effective gravity is almost twice as much. This amplifies the difference between the weight of the hot air and the weight of the cooler air around it, and so the hot air rises faster, making a longer flame.
So this didn't seem all that different to me, except that it's more steady, and that's Cliff, right?
Yeah. Hi, Cliff.
Hey, Cliff. Thanks for joining us.
Yeah. Well, what it looks to me like is that it looks much more cylindrical. It looks much more like a pillar instead of the bulge of the flame shape.
Oh, I see the teardrop kind of.
Yeah.
And the other ones seem to flicker more. You know, we've watched this a couple times now.
Right.
And so, you know, interestingly enough, if you go to a place that has higher gravity than the Earth, your flames might be different
Yeah.
there too.
A campfire won't be the same in a 2G world.
No?
It'll look more like a column of flame rather than,
Yeah.
you know, so.
So let me go ahead and I think they do a comparison between the regular flame and the low gravity, supposedly. You know, because it's a simulation. It's not
Right.
actually low gravity here.
And
Oh my goodness. Look how that flame just wafts in 0G because there's much less buoyant force to carry away.
now,
And so
Yeah, he's
the
moving it
combustion is not
around.
as good. You
yeah.
see a lot of
Now, if
smoke
you see when he moves it
coming out
up,
of that candle.
he moves it up as fast.
That is
At the same
incredible.
speed that the butane's coming out, and you get that same dome shape that.
Hey,
So we still have the gas flow, so this is why the flame is not circular.
Oh, he
he-
mentions it.
Yeah, he just.
It's not a
Yeah.
sphere, but it looks very strange.
In 0G, the hot air is still less dense than the cooler air, but now there is no weight and no buoyant force, so the flame doesn't rise as high. This flame still maintains some of its shape because of the flow of fuel from the lighter. Otherwise, the flame would form a sphere, like on the space station, where it's very difficult to maintain the combustion
And there's the cosmonaut
Yeah.
video again.
reaction because it's hard for oxygen to access the fuel with all of the combustion products getting in the way. So
So that was pretty interesting, and you can certainly watch the whole thing for yourself, because I will give you that link too.
Mhm.
All right. So there it is, and those should be clickable in there. And what's next?
Something else.
Yeah, this was another viewpoint of that experiment. I thought that was. It's really a fascinating way to study this. It's very controlled. It's even on the edges. I think you're not seeing the flame.
Well, I think that really faint thing is the flame.
That's what I'm saying. This is probably the flame, but you just can't
Right. But
really see it unless
if
you're
it-
looking for it.
and if in the dark area you can see it. If that was normal
Right.
lighting, I don't think you'd see that,
I think you're right.
which makes it, you know, kind of a little bit more dangerous.
Right. Yeah. Yeah. Exactly. Because if you can't see it, it could move around and you wouldn't even know. Just like the man who was on fire, but
Yeah.
nobody really knew.
Yeah. And the fact that apparently it produces carbon monoxide and formaldehyde.
That's not good.
Yeah. You know, I would, you know, for fire detectors, you could just look for formaldehyde or,
Oh.
you know,
Yeah.
we already have carbon monoxide detectors.
Mm-hmm.
You could use those.
I see another comment.
Oh, yeah.
Cliff said he was here recently at Star Stuff as a speaker. I didn't get to go.
Ah,
Was that oh, this guy here, this
yeah.
no, not this one, the previous one, the guy from one of these guys, this guy, I don't know who that is. Tell us who that is, Cliff. So this is another, it's really short too. I'll run this for you. It's they're very definitely thinking about safety and how to figure this out. But yeah, you're right. Using those detectors would be.
The crew also spent some time studying fire up in space. Fire behaves completely differently up in space in the vacuum and the absence of gravity than it does here on the ground. The crew worked on a device called the Combustion Integrated Rack, which tests different fuels and finds out how they combust. And the crew spent a significant amount of time working on something called BAS. This is burning and suppression of solids. This takes a look at how flames burn up in space. It's quite a bit different whenever you put out a fire up in space versus here on Earth. Typically what happens here on the ground, you would aim the fire extinguisher or the suppressant at the base of the flame. This is because that is where the flame is the most stable. It's where the flame is basically born, where the oxygen and the air enters the flame and sort of creates it. But of course, up in space, you don't have that. So the BAS experiment takes a look at how the fire behaves and how someone would put out that fire up in space.
Pretty cool, huh?
Also spent some time.
Sorry. All right, and this is another one in mirror, but this one, look at this candle's anchored, and I kind of have a thought about this. Well, I'll just run it. It's only 27 seconds because you've got a dome, but it's flat on the one side. I wonder if you could actually create a light source that's got the fuel in the very center of it. That might be interesting.
Well, one of those experiments with the round drop that they lit was completely spherical.
Yeah.
Okay.
So yeah, you see that edge there, but that's where the candle is. You got another comment I noticed.
Oh. Yeah.
Dylan O'Donnell. Okay.
Okay. Yeah.
Good. Thanks for that. I appreciate it.
Yeah.
Guy with the beard. Okay. I guessed it. All right. So I think I have one more. Oh, these folks did some interesting. Yeah. What?
Oh no.
Okay. These students did some interesting work. Let's see. They created this triple box thing to do an experiment with fire. I think that's really interesting too. But again, it's a little bit longer. I'm going to grab that link for you and share it in the chat because we want you to go and look at these things too. This is to pique your interest. So the other part of this was temperatures on asteroids, and I actually didn't find that much.
Yeah, I do know a bit about it, so.
Yeah, I would say there's some things to consider. Like, where is it? Is it in space? Is it coming through an atmosphere? And what is it made of? The composition. Also, if it's anywhere near a star, you know, the sun side's going to be hot and the space side's going to be cold. But yeah, what were you thinking about it?
Okay. Anything. Well, okay. 3 ways to transfer heat. One is direct transfer. I mean, you know, I touch her, you know, if I'm hotter than her, heat transfers. That's direct transfer. The other is convection. And that's where you heat up the air around you, it rises, more air comes in, which is essentially transfer to the heat, to the air around you, but it's replaced.
Also how a candle works.
Yeah, how a candle works. And it's also why a wind that even in a warm day will make you feel cool, because it blows all of the air that your body's heated up away from you.
Not if it's off the desert.
Right. Yeah. But the third way is radiation, and that's infrared. I mean, anything that's hot radiates heat.
Yes.
And it doesn't really matter what's nearby; it will radiate the heat. Now, if it's in warm air, it'll gain more heat from the air than it radiates, but it'll still radiate. And so you get an asteroid or the moon, anything in space without an atmosphere to keep stuff in, is constantly radiating. Now, the sun heats one side of it. That makes that side very, very hot. So you can have 200-degree temperatures on the side facing the sun, but the side away from it, because there's so much mass in a moon or most asteroids that it gets very, very cold. It's radiating heat in all directions faster than it's getting some heat in on one direction. So eventually it cools down to, near absolute zero, whatever the local space temperature is, which is, 3 Kelvin or something like that, 3.5 Kelvin, which is way low. So eventually it'll get there. Eventually the Earth would too. It's just we have a nuclear furnace in the middle that is making heat. But even if that went out, it would take centuries, if not thousands of years, for the Earth to cool enough to actually notice.
Well, and with the atmosphere, it kind of evens things out.
It keeps some of it in too.
Right.
So if the sun went out, we wouldn't actually freeze to death right away. It'd take a while. But so
I start first.
So an asteroid, it would really depend on if you're on the sunlit side and the sun's been on it for a bit, then you'd cook whatever you touched against it. If you're on the side that's been away from the sun for a bit, you'd freeze whatever touches it, because the bulk of the asteroid, just like the bulk of the moon, is near absolute zero. And the moon is actually a little bit warmer simply because it's bigger and it hasn't gotten rid of all of its heat yet. But an asteroid's small enough that it probably has. Now, if it's nearby Jupiter, tidal stresses might heat it up some.
Or radiation.
Yeah.
From Jupiter. So I do have a video. I'm not crazy about it, but let's go ahead and run it. You can decide for yourself, of course. And we'll mention some things too.
Hello, Earthlings. Did you know that most asteroids do not have significant atmospheres, which is why temperatures on their surfaces can be so extreme? Without an atmosphere to regulate temperature, asteroids can experience large temperature fluctuations between day and night. During the day, asteroids receive direct heating from the sun, causing the surface temperature to rise significantly. At night, the asteroid loses heat rapidly due to the absence of an atmosphere as a thermal insulator, causing the temperature to plummet. These conditions create a harsh environment on the surface of asteroids, affecting the physical and chemical properties of these celestial bodies. Hello, Earth.
So, yeah, to say it's day or night,
I think
a little strange, but it's an AI generated thing. I think it could be refined, and that's the thing about AI. I think you want to, if you're going to work with it, you create the thing and then you review it and you update what you think.
And that's why I talked about sun-facing side versus the side away from the sun.
Yeah, that to me is a better way to describe it.
Yeah, and also just be aware that space itself is a very good insulator. Do you have any videos that talk about the freezing in space?
I don't think I have anything.
Okay, because
handy, prepared.
Because unlike a bunch of the movies, you aren't going to freeze if you get into space. You'll suffocate, but you won't freeze, because space is a very good insulator. Now, eventually you will.
Yeah.
But not before you're already dead.
Well, that's a great segue into heat versus temperature, but let's take our comment first. I see Janie's got it's basically limited.
Yeah.
I think it's a great place to start. It's sort of like your first draft.
Yeah.
It's a good way to do a first draft. So heat versus temperature. And I remember earlier this year, there was something about high altitude, and they were saying it isn't actually cold, it's hot. The trouble is that there aren't very many molecules there. The higher you go, the fewer there are. So because there's fewer, you don't actually get the heat. So I've got some videos. Did you have a comment? I can see you thinking.
No, but we'll get into it. I have a couple things to say, but we'll see.
Okay, so I did find a few things on this, and this guy seemed pretty good. It's a little bit long too. I don't think I'll go into it too much, but I like to get descriptions from different people because you can get sort of a different. It's like, oh, okay, and then you get it a little better depending on who's describing it. So let's give this guy a shot. And he's a professor. He's actually a professor.
Concept. We can start with temperature, like the temperature outside today. It might be hot, it might be cold, but in science, we want to quantify everything that we can. So saying something is hot or cold just isn't enough. We want to be able to say how hot or cold with numbers. But that begs the question, what is it that temperature is physically measuring? Temperature is measuring the amount of heat energy available for work in a system. And heat energy is related to the average kinetic energy of the atoms and molecules within that system.
Okay, temperature. And I've also heard it described as sort of this, the summation of all of the things. Like if it's air, if it's water, some molecules might be hotter than others, but it's the average of all of them.
Is
that a comment or is that a?
No.
Okay. All right, so that's temperature. All right, so let's see what else he's got to say.
We know that greater kinetic energy means objects will move faster. And this is true of molecules in the atmosphere, just as it is of macroscopic objects. So higher temperatures simply mean faster moving particle.
Okay. So, yeah, you got a comment?
Ronald, hey, Ronald.
Hey, Ron.
Yeah, I never thought about outer space being a good insulator. That's the whole idea of a true thermos bottle. It's insulated by a vacuum between the inside and the outside layers of glass.
Right.
Yes, because you cannot have heat transfer and you can't have heat convection. So it's only heat radiation.
Ah, yes. Okay.
And in the thermos bottle, one side will radiate heat.
Do you want to show yourself?
Okay.
Because he's doing the fingers.
Okay. In a thermos bottle, once you've got one side radiating heat, and the other side will radiate heat also, and they kind of will keep each other from. It'll slow down the transfer of heat. It's kind of like the way a two-pane window works.
Yeah, isn't that a vacuum as well?
No. It would be much better if it was a vacuum. However, it'd be much more fragile. You whack one side and it wants to break inward.
Oh, that makes sense.
Yeah. So yeah, it is. Vacuum is a very good insulator.
And thanks for making your comment and for being here, Ron.
Yep.
Appreciate that. All right, so we want to show. Okay. Yep. There we go.
This kinetic energy of motion is distributed amongst translational or side-to-side motion, rotational or spinning motion, and vibrational motion, where the covalent bonds in a molecule bend and stretch.
Yeah, he's getting a little technical there, but those are the different ways, so that's okay.
Heat will flow from hot objects to cool objects because as the particles move, they will impart some of their kinetic energy onto other particles through collisions. This will continue. Is
that going to be true in the thermos too, with the vacuum in between? That's true, right?
No, because that's transfer.
Yes.
You can't transfer through a vacuum. You can only radiate.
Okay. All right. Thank you.
To occur until the whole system is at the same temperature in a state called thermal equilibrium. This is how thermometers measure temperature. Heat from the environment will be in contact with the thermometer and flow into the thermometer fluid, causing the atoms to gain kinetic energy, and the column will expand until it is in thermal equilibrium with the environment, thus allowing us to read the temperature in one of our man-made units. We must bear in mind that all phases of matter expand with higher temperature, whether solid, liquid, or gas.
Yeah, I really like that he goes into how this works with the different versions. So that's pretty cool. I think there's just a little bit more of this one, and I have a couple of other. And let me grab this link for you too.
Yeah.
Because this is
he
really
does a
good.
good job of it. Yeah.
Yeah, the whole thing I think is very worthwhile. We're just seeing the middle part of it here. All right, so let's see what else he's got for us.
This phenomenon is called thermal expansion. Energy is transferred as heat in a wide variety of processes. When a collision occurs, there is usually some heat generated. Friction can cause heat as well, which is why your hands warm up when you rub them together vigorously. In each case, we are considering the kinetic energy of the particles and the transfer of some of this energy to other particles as the definitions of heat and heat transfer. Heat is therefore a kind of energy in transit and will be measured in joules just like any other kind of energy.
All right, so I think that's enough for that one. I'm trying to find a simple way to describe it. Maybe this will do it. This one's really short too. It's about 55 seconds.
Imagine trying to race a turtle and a rabbit. That's kind of like understanding heat and temperature. So, temperature is like a speedometer for molecules. It shows how fast particles are moving or vibrating.
I think this one's nice because it's got a fairly graphic, presentation for you. So,
in a substance. Higher temperature, faster movement. Lower temperature, slower. But how slow can it get? Well, if molecules stop moving completely, that's 0 Kelvin or absolute zero. Not 0 degrees Celsius, folks, but 0 Kelvin. So temperature is the average kinetic energy of molecules. But heat is the energy that moves from one place to another, always flowing from hot to cold.
Okay, I think that's a pretty good way to do it. It's measuring it and movement of it. Does that sound right?
Right. And
okay,
two things that have different amounts of heat when they come into contact will eventually have the same temperature. Not necessarily the same heat, but the same temperature. So
delve into that a little more. Heat's the moving, right? Because if they do, if it does reach that equilibrium, they've moved to the same.
And some things can hold more heat than others. Think water versus wood.
Okay.
Water at 100 degrees will basically scald you. Wood at 100 degrees, you could pick it up. It'll feel hot, but it won't hurt you.
Because it hasn't combusted yet, so.
No, because it doesn't hold as much heat.
Okay.
It doesn't hold as much heat. So.
That's the moving.
Right, yeah. So it doesn't take or let's take aerogel. That's an extreme example.
Yeah.
You can make it 1,000 degrees Fahrenheit.
But you can pick it up still.
And hold it in your hand because there's so little heat there that it will very quickly transfer the little bit of heat that it has into your hand until the temperatures are the same. So they'll match temperatures. When you put things, thermal equilibrium that he talked about is matching temperature, not heat.
Is that the same thing with there's just so few molecules out in space? And aerogel is a very fluffy.
Yeah, loose. In fact,
it's like the least dense solid.
Right, yeah.
In the world or something.
Yeah. And so it's the thermal capacity of something, that, you talk about how much heat something can hold, and they measure that by putting it against water, usually is what they use for measuring.
Okay, and I did grab that link and put it in there. I've got just two more I would like to present to you. And this one's very, very long. I'm not going to really delve into it, but I do think it's very enjoyable to listen to Neil deGrasse Tyson. And in this case, he is talking to someone and he's going to...
between heat and temperature.
Yeah.
They are not the same thing.
Yeah.
Okay, so you have already, you're right, because if you say that this is a source of misunderstanding, then I am the source.
All right, let me grab that link too.
Yeah.
Because I think that's definitely fun to watch.
Yeah, he goes more into, in fact, he gives some pretty good examples of how something can hold a little bit of heat, but be a high temperature and still feel, and still not cause you problems.
And here's another source. I didn't hear about Mamatrix before, but it's nice to have, like I said, different perspectives on how this works. Again, I'll just run it very briefly.
Heat versus temperature. Now, before I dive down into the details, I would like to start by simply defining the two. Let's start with heat. Heat is energy in motion from a high temperature entity to a lower temperature entity. Heat is measured in joules. Temperature, on the other hand, can be defined as a measure of internal energy of the entity. Temperature is measured in Kelvin, Celsius, or Fahrenheit.
I think that's a pretty good summation.
Yeah.
So this thing, it's just my research. Okay. So fire in space is definitely different. In some ways, it's not quite as problematic, and I think in some ways it is. I mean, because if it travels around and you can't see it, then you're going to have a problem.
Yeah, I don't think it travels so much as just it's, spherical. So it doesn't have a direction, but it burns cooler. So in that way, it's not as much danger. But since it's burned cooler, you might not even see the flame, which means that you could get yourself hurt without knowing it.
Right. Yeah. So, but yeah, I think there's a lot to know about that and keep learning about it. Like, in fact, one video they were saying, oh, this guy's an expert on it, but he was completely baffled by seeing flames in space, seeing fire in space. We got another comment I saw. Looks like from Cliff.
Yep. You can heat up a shuttle tile white hot, and after a few seconds, pick it up in your hand. Yep.
Right.
Yeah.
Yeah. Why is that?
It has very low thermal mass. It doesn't hold much heat.
Okay.
So it can get very hot. But because it's not holding, so it'll match the temperature of the outside, but not pick up very much heat, which means that the stuff on the other side of it that's touching it, the shuttle side of it, it's very hot. It has a high temperature, but low heat. So it'll heat up, it'll transfer that heat to the structure that it's on, but there's very little heat to transfer.
Okay.
So that's why insulators, thermal insulators work well.
In any case, I am so glad you brought that up, Janie, and I hope that has helped some, or at least given you some options to look at. Yeah. And the great thing about video is you can play it over and over again. It never gets tired. It never complains.
Yeah.
You can stop it. You can start it and go back and forth.
Yeah.
It's a wonderful resource.
Yeah.
So yes, and if anyone else has a suggestion ever, we would love to hear about it and see what we can.
Yeah. If you've got a topic for us, Cliff says that there's a video on the shuttle tile. I'd like to see that.
Cool.
If you find it, shoot it to us and we'll put it out for people.
Yeah, that'd be awesome.
Oh, and
oh, good.
Yeah.
Yay.
Yep.
Thank you. It's really fun to do the research on
it. And there's probably, if a scientist watches us explain this, they'll probably be cringing. But, because we don't know as much as they do, but we learned maybe more than some of you guys know. So we're helping raise the temperature of the conversation.
It's a temperature or heat. All right. You want to do this part?
Well, for some people, it doesn't take very much learning to really increase their level of knowledge.
Okay. So, all right.
So I'd say temperature.
Okay.
Okay, some stellar events this week, November 15th through November 22nd. On November 15th.
That's today.
Yep, today, full beaver moon. I don't what was wrong with their minds.
Not everybody names these things. Cliff is constantly amused by our names for full moons.
Yeah. And Uranus and the moon are in conjunction, which, okay. Let's just follow the.
Keep going.
November 16th, Saturn is stationary, or appears stationary at least, because it doesn't actually stop. And Uranus is at opposition. Also, hang on.
Oh.
So you must have been to Texas.
Texas? I don't get it.
My having fun with the beaver moon.
Oh, I see. Okay.
I think that's what he's talking about.
All right. Okay.
Also, Mercury is at its greatest western elongation, which puts it 22.5 degrees east of the sun. Look for Mercury in the evening right after the sun sets.
Yeah, right after.
Yeah, which means that you probably want a pretty low horizon to see it.
Oh yeah, definitely. And Venus is over there too, so.
Yeah, Venus is quite bright right now.
Yeah, very bright.
Yeah, Pleiades is 0.1 degrees south of the moon and is in occultation. And Venus is at opposition. We've got two different.
That says.
Or Uranus.
Wait, why do I have it twice?
Because we've got two different sources.
Okay.
Yeah, I thought so.
That's
but
right.
I didn't see it the second time we went through it.
Yeah.
November 17th, Jupiter and the moon are in conjunction. Jupiter is 5.6 degrees south of the moon. And the Leonids meteor shower peaks. Its date range is November 6th through the 30th.
So now, basically.
Yeah, and it peaks November 17th through 18th.
Couple of days.
Yeah. Best time to observe is after midnight. It radiates from Leo and is 10 to 20 per hour, which isn't a great rate, but hey. So if you see something flashing through the sky at, during these days, these few days, yeah, it's probably one of those. Its source is 55P Temple Tuttle. And the moon is 16 days old and is waning through, though still bright, and it appears in the night for almost all night.
Yeah, it's 2 days after the full moon. So basically, full moon comes 50 minutes different each night, right? So instead of like full moon, sunset, the moon comes up, it's going to be about 100 minutes after sunset. But that means it's in the sky for the whole night, and it's still pretty darn
so
big.
It'll make it pretty hard to see the Leonids.
I think so.
Yeah. November 18th, the moon rides high. November 19th, Pollux is 1.9 degrees north of the moon. And in 1969, Apollo 12 landed on the moon. Our second manned flight landed on the moon. November 20th, Mars and the moon are in conjunction. Mars will be 2.4 degrees south of the moon. On the 22nd, it's the last quarter moon, and Regulus is 2.7 degrees south of the moon.
That's a busy week.
Yeah, it is.
They're still going.
Next week's not very busy.
No.
Also on the 22nd, Friday night show, we have a guest. We've been hinting at who, and we'll confirm that shortly. Find us Fridays at 9 p.m. Pacific time on the Everyday Spacer Facebook page and the Everyday Spacer YouTube channel.
What inspires you the most for the coming week? So if you or someone you know has done something interesting involving space exploration, science, or astronomy, we'd love to share our live. And next week we will. Join us again next Friday, November the 22nd, when Jeff Creason will join us and we'll chat about his interesting journey in the space industry. And I saw some more comments, so let's address them.
Ronald, a reminder, the Starship is scheduled to launch on Monday, November 18th at 4 p.m. Texas time.
Excellent.
It will be interesting to see how the heat tiles hold up during re-entry.
Are they heat tiles or temperature tiles?
Okay. Yes, the moon can be a pain at times. Yeah.
And for you, it's mostly clouds that are a pain, I think.
Well, the moon lights up the clouds.
Yeah, that's
Makes it harder to see through them. Janie says, I appreciate all the research and video links, guys. You're awesome. Well, thank you, Janie.
Thank you, Janie. We really appreciate that. So, next week we have a guest. I can't wait because we've known Jeff for a long time.
Yeah, I mean,
he's a really interesting guy and done some really cool stuff that when I was looking at it, I was like, oh, I didn't know that.
In some ways, he's one of the group of people that are responsible for the commercial space industry right now. So.
Oh, thank you, Don.
Yep.
Appreciate that. And I know you're up late. All right, so let's do a shout out. Don was here and Janie was here, and
Cliff was
Cliff and Ronald, thank you so much for being here, folks. Did
and
we?
Scott.
Oh, Scott was here, right?
Yep. And
it's always a better show when you are here and you make your comments and help us find out stuff.
Yep.
Very, very helpful. Yeah. Yep, that was it. Good. All right. So anything else from you?
Nope.
We will continue to watch for your comments as well. Thank you so much. Have a great week, folks.
Yep.
We will see you next.
And if anyone has an idea for a topic, let us know. We'll do the research for you.
Well, it always, we learn good stuff whenever you have an idea, and we can all help each other out.
Yep. Okay.
Thanks a lot, folks.
Good night.
Have a great week. Good night.